All right, so I'm Wendy Pinena, and I'll be chairing the session this afternoon. Those of you that heard my chairing session last year, there's going to be no funny business this year. Let's all keep it together, please. All right, first up, we've got Rafiwe, and she's going to be telling us, well, she's going to be looking at assessing nitrogen dioxide in the high-felt troposphere. Over to you.
Thank you. Good day, everyone. My name is Rafiwe Kakane, and today I'll be telling you a little about one of the objectives that we investigated during my PhD research, which was assessing nitrogen dioxide in the high-felt troposphere. Nitrogen dioxide forms part of the pervasive air pollution and the cause of some of the associated air pollution consequences. Nitrogen dioxide is not in itself a greenhouse gas, but it indirectly contributes to the warming by forming tropospheric ozone, which is a greenhouse gas. Globally, nitrogen dioxide emissions from various sources have been increasing, especially in developing countries such as South Africa. With the increasing atmospheric nitrogen dioxide concentrations comes increasing environmental and population health issues such as acid rain, soil and water acidification, smog, increased algal blooms in natural water systems, biodiversity loss in sensitive habitats, and exacerbated human respiratory conditions such as asthma and chronic obstructive pulmonary disease. The World Health Organization has emphasized that nitrogen dioxide is a major pollutant of concern. So the high-felt area, as you can see from the map, the high-felt area has been identified as a pollution hotspot in Southern Africa with the Mpumalanga high-felt, those green triangles there, the Mpumalanga high-felt having most of the coal-fired power stations, which are more than the other high-felt provinces. So in addition to the coal-fired power stations, there are other sources of NO2 in the Mpumalanga high-felt, such as emissions from vehicles, biomass burning, and burning from surrounding settlements. The NO2 concentrations in the high-felt are reported to exceed the national air quality standards. Hence, it is important that we understand the concentrations in that region. These concentrations are comparable to emissions in developed and highly polluted regions such as North America and Southeast Asia. This here is an image of tropospheric NO2 concentrations over Southern Africa, just to show the elevated concentrations over the high-felt. And this is an image from the 31st of August 2025. So, however, with all this that's been mentioned, South Africa has scant air quality information due to the lack of resources to measure the trace gas concentrations. So this is a map showing ground-based instruments called Pandora. And as you can see, the Global North has a lot of these instruments, but the Global South does not. In Africa, we actually have 2 operating instruments, and they are both in South Africa, and I worked on one of them for my PhD. So it is important to understand the distribution and transport of the emissions in the troposphere, since the troposphere is the layer of the atmosphere where most of the emissions are released and also where the air that we breathe is. For that reason, we worked on filling the gap of scant air quality data in South Africa by leveraging tropospheric nitrogen dioxide data from a Pandora 2S ground-based column integrating instrument located in Wakkerstroom in the Mpumalanga province of South Africa. And we also use space-based remote sensing data obtained from Tropomi on board the ESA Sentinel-5 satellite. This study was done at Wakkerstroom, which is a small town in the Mpumalanga high-veld, located downwind majority of the coal-fired power stations, and also located close to the Gauteng-Tshwane metro, which is highlighted in blue in image A. So we use the ground instrument, the Pandora, in max DOS mode, and a satellite instrument, the tropospheric monitoring instrument, Tropomi. The Pandora instrument is a sun photometer with a dual spectrometer system. It measures trace gases in the ultraviolet and visible spectral range of 270 nanometers to 530 nanometers, and in 400, and also from 400 to 900 nanometers. The instrument scans the sky at various elevation and azimuth angles. This sped up video that you just saw shows how the instrument moves as it measures the tropospheric NO2 concentrations. The different elevation angles make the instrument sensitive to different levels in the atmosphere, so at different altitudes, thus giving us integrated tropospheric NO2 concentrations at about 6 kilometers above ground. The tropomi scans the Earth from space, so it looks from the top to the bottom, and it scans the entire Earth daily, and it has a local overpass at 1330 at each location, and it gives us concentrations of the full tropospheric column. Right. I'm not going to go any further into the specs of these instruments. If you want to know more about the nitty-gritties of how these instruments work, we can have a chat during the break or after the conference. Otherwise, catch me outside. So now I'm going to give you some of the findings. There are a lot of them. So these findings are as follows. The comprehensive results can be read from our published manuscript. I will put it on the Slack. So we found peak Pandora measured NO2 concentrations in spring and in summer. So what's the big deal about that? Hey, we found peak concentrations, and so what? So our findings from the ground instrument measurements are actually contrary to the literature and the satellite-derived concentrations. And the literature and the satellite-derived concentrations showed elevated NO2 concentrations in winter. But we found them in spring and summer. And this can be attributed to a few things, such as the transport of air masses to the site where we actually measured the concentrations, and also to the stable atmospheric layers in the high veld, which caused the mixing of the NO2 in the tropospheric column to not be as good at that point. So in this figure, which was derived from high split, which is an air mass backward trajectory model, we can see that, so from the top, yes, the top arrow, it's 54%. So 54% of the air mass trajectories that arrive at the site are actually from the east of the site. And so these air masses are loaded with NO2 concentrations from southern Mozambique, Eswatini, and also recirculated concentrations from the high veld, including emissions from coal-fired power stations. So this study also provided insight into the combination of the various sources that contribute to the NO2 concentrations measured at the Wakkerstrom site. The image that we have here shows the active fires during 2020 in parts of southern Africa, and this shows that in addition to power stations, there are also biomass burning emissions, wildfire emissions, and other emissions that are not mentioned today. Okay, so we have more data, we have a better understanding, and then what? So studies like this one, they contribute to the understanding of pollution, one trace gas at a time, one site at a time, and also to the associated consequences of air pollution. In the past few hours, from yesterday till today, it has been reiterated that air pollution is one of the main drivers of biodiversity loss in certain habitats, and that increased temperatures increase bird mortality in tropical forests. And also it has been reiterated, or also it has been mentioned that the adaptation of biofires to pollution is one of the research questions that are still going to be investigated in the future. Therefore, it is important that we understand the sources, heterogeneity, and the dispersion of criteria pollutants such as NO2. Thank you to all the sponsors, the software engineers, instrument calibrators and operators, and my supervisors for making this study possible. I appreciate you. Thank you.
Right, thanks, Refiwe. Any questions? Concerns, complaints, suggestions? Yes.
Thank you for the presentation, Refiwe. I just have a question around where our emissions are going. Since you said most of the nitrogen emissions in your study site come from Mozambique and Swaziland, where do our emissions go then?
Oh no, so they are just a contributing factor to the ones that we are also emitting. So I mentioned the recirculated emissions in the Highveld, which would come from the Gauteng-Tshwane Metro, and they would also come from the power stations, the coal-fired power stations in the Mpumalanga Highveld. So in addition to that, with the emissions from southern Mozambique and Eswatini, then we see a higher concentration of the NO2 at that particular site. So it doesn't mean that our emissions are not part of what we saw. They definitely are.
Any other questions?
Sure, this is really next level, almost one could say sci-fi, but I want to, in contrast, maybe ask a stupid question, is that the nitrogen fixation by lightning, especially in Highveld, that cannot lead or in the equation of NO2, as well as even getting more nitrogen out of the atmosphere, or is that not really significant? Is that too small an amount to take into account in the whole nitrogen balance, the fixation of nitrogen by lightning?
So it is something that has to be taken into account because of the whole nitrogen cycle. However, for this study, we do not look at that. But yes, it also contributes, yes.
Okay, we have time for one more question. Aha.
Hi, Refiwe. My name's Glynis. I noticed your study was in 2020. Do you think that was obviously over COVID period? Do you think that the quality and the levels that you measured would have been affected because there was less activity, less travel during the COVID period?
So it could have. We did not look at so we didn't have data for 2019, therefore we could not have compared the nitrogen concentrations in 2019 to those that we found in 2020. However, we did look at the 2021, and the 2021 concentrations show that as much as the elevated concentrations were not necessarily seen in spring, but they were seen during the transitioning from winter to spring, and also from spring to summer. So yes, COVID could have played a factor, but we did not have 2019 data in order to compare.
Great, thank you so much. If you've got any further burning questions, she'll catch you outside. Okay, next up, we've got Stephen Johnson. Has anybody read the title? Big Data's Big Daddy, Aerial-Borne Multi-Sensor Data Collection Beyond the Curve.
Hi, many of my old friends, young friends, new friends, and to-be friends. Lovely to see you all. Good one. Today, I'm going to talk about big data's big daddy and aerial multi-center data collection. About 40 years ago, a young man set out seeking adventure flying an air balloon across many parts of southern Africa. And he fell in love with its landscape and its wildlife and its whole sense of vastness. Skip Darlington, an American. And in the intervening time, he put together a team of people that looked at trying to use aerial-borne platforms for conservation. But around that time, 40 years ago, there was a young man that was just starting his career in national parks in Zimbabwe, and that was me. And over the years, we communicated somewhat, and it's in the last 5 years that we got together and saw the potential of actually taking this further. So what we bring you today is an innovation that can revolutionize conservation research that we feel. It's an airborne platform that can stay aloft for 10 days and operate 24 hours a day. And on board is high-tech, high-resolution sensing and a supercomputer that goes with it. We call it the sensible option. Now, innovation is when you take two things that already exist and put them together in a new way, and that's what we feel we've done. But who are we? We are an NGO that looks at enhancing environmental intelligence and research. We're a team of aviation, sensor, and environmental management professionals in our team. We support research to collect specialized, aerially sourced data, and we focus on biodiversity, environmental management, and sustainable development. Our area of expertise is that we've developed and patented an autonomous, remotely piloted airship that is equipped with cutting-edge sensors that survey the ground below in flight. Now, these sensors can collect and image thousands of square kilometers on each mission, gathering data from below, that is, across a wide range of wavelengths and radio frequencies with superior resolution and at a fraction of the cost of satellites and other similar platforms. So from a research point of view, our problem was that we saw that aerial collection of data is constrained by its high costs, especially with airplanes and helicopters and things, the short aerial duration, the limitation on the scope of the data collection equipment itself, the limited resolution of the data collected. And we saw that this constrains a lot of research. And so we looked at the various options of satellites and aircraft and ground truthing, and there's still high costs there or problems in the times that you can actually collect data. And we looked at resurrecting and enhancing old airship technology so that it's extended with its duration of being aloft, putting on board high-tech sensors, 8 of them, maybe 6 sometimes, with an immediate onboard and analytical capacity. So the data sensors can collect the data and it's analyzed on board and then it's relayed to a ground station. And it can be collecting specific data that you program it to collect. And we feel that this will enhance a lot of research that is going to be available. So we have an airship that flies at an altitude of between 1,200 meters up to 10,000. It can cruise at 35 knots, maximum 60 knots, and stay up in the air for about 200 hours, which no airplane or drone or anything like that can do. And we can cover vast areas at a time. But our special competitive advantage is Discovery One, our sensor suite, which uses near-infrared high-resolution spectroscopy, thermal imaging, and daylight RGB with our onboard AI processor. Now, it sounds amazing, but it can operate at 25 trillion operations per second for real-time analytics. Okay, I'll talk about that later if you're interested. It provides 3D reconstruction and geolocation with stereoscopic imaging and additional things. It can have bioacoustic microphone arrays and liminal lighting for operating in certain night situations. We looked at a number of different imaging and data gathering sensors that are available, and we have compared everything with what we've been able to produce, which we feel is our cutting-edge offer. So as it flies and has a radar frequency operating below it, it can cover a swathe of 60 kilometers, seeing 30 kilometers on either side, and can detect objects, especially moving objects, in high definition. So, for example, if we were looking down on a suburb and looking at a mall with this parking lot, we'd be able to see certain vehicles and even identify these number plates and things like that, even at night using thermal imaging infrared equipment. Our secret sauce is our shortwave infrared sensors. Now, if you look at this as an ordinary photograph, and if you really look hard, you might see some vague images of a building behind. But with our equipment, we are able to transform that so that it penetrates any smog, smoke, mist, or even snow. We've tested it even in snow. So that's the kind of sensing you can see under very adverse conditions. Its resolution is amazing. At 4 kilometers away, what would be a real-life example on the left is the image we would be able to see at 4 kilometers. That's 30 blocks of a city. And even at 17 kilometers distance, we could program it to identify that if something looked like that, it would be an elephant and very likely its calf. So if we were looking at what can we do with this, we can use it for general population counts, tracking herd movements, identifying sick or injured animals, assessing health and fitness, assessing conditions of grazing and vegetation, and even doing real-time and phase-time vegetation assessments. And we are now exploring machine learning to be able to even track individual animals in a herd. It can monitor endangered species as well, which is an important aspect that we're offering. And the stereoscopic sensors I mentioned before are used for tracking birds and marine animals from the airship on 20-meter-long carbon fiber rods with sensors on the edge. And they can geolocate resting birds and birds in flight and bring to life a whole different area of research. So what's our possible contribution with the findings that we've had? We can enhance early threat detection and crisis response, such as in human-wildlife conflict. It can support governance and enforcement activities, such as anti-poaching, illegal fishing, illegal logging, mining, and for either real-time response or for strategic planning to go back to at a later stage. We can improve ongoing management research through monitoring, predictive models for climate, biodiversity, and resource management. And also, it can enable continuous low-cost change measurements in carbon offsets, hydrology, habitat, and protected areas. From a social side of things, we work with communities to ground truth of some of the research and findings, provide data to them for some of their challenges, and even share data with them for the agreement for local enhancement, and empower communities with this data and help them build their leadership for effective long-term management. So the pain points that we want to avoid or help you avoid is eliminating high aircraft costs, minimizing the data gaps from cloud cover and the revisit delays that you have in satellites, reducing the processing lag that we can actually operate in real time, and it also provides contextual big picture missions using our field sensors. So we bring you an innovation that we feel can revolutionize conservation with our airborne platform and the high resolution sensing. So if you need to and you're interested, please contact me and we can discuss how this might help you with your research and help with our sensible option. Thank you very much.
Thank you, Steve. Any questions?
Hello, thank you for presenting a fantastic subject, but one thing that concerns me is the fuel that this airship uses. What would that be?
So it's a combination of renewable energy with sensors on top of the airship itself from sunlight, etc. And there is some onboard diesel or aviation gas that can propel it. So it does carry a stock of that so that if it needs to, in adverse conditions, be able to move around and not get kind of trapped in certain circumstances.
Thank you very much.
Lots of questions.
I'd like to just thank you for a very interesting presentation. I'm curious about the resolution, the ground resolution that the sensors can provide for imaging. And you showed us a picture of an elephant, which definitely looked like an elephant. You also mentioned that it could read car registration plates. And to me, those seem like very different kind of orders of magnitude of resolution. Do you actually have a figure, in terms of pixels per centimetre kind of thing that would help us understand what could actually be seen on the ground?
We have that, okay, and I can give it to you virtually immediately after this, but I don't have it in my head right at this moment.
Okay, that's fine, thank you.
Yeah.
Hi. What's the reason for doing the processing on board? I'm just worried because now getting your raw data goes there, processing takes place, but heck, your airship just crashed. You've lost your raw data. So what was the thinking there?
Okay, the good question. The processing can take place at such a high rate, and that's huge data that's being collected. Okay, and you can program it to only send down or up to through satellites or to a base station certain information that you need. Okay, so instead of trying to dump all of that huge data at a time, it stores it up there, sends you what you need at that particular stage, or just leave it up there, storage, and when you land, you can get access to it. So that's the reason for onboard.
Same problem if your machine crashes, though. But I'd like to chat to you afterwards then.
Sorry?
I'd say it's the same problem if your airship crashes. It's still lost the raw data. So we'll chat.
Yeah, but that happens in a light aircraft as well, so same situation. Sorry? The airship. It varies according to what you need and what payload you want to carry with it, okay? It can be from about 10 meters up to about 40 meters. They can be very, very large. Yeah.
Hello, I'm Simone. This is a very fascinating product, but I am curious about the risk of hacking. It has a lot of benefits for conservation, but when monitoring endangered animals, what's the risk of this being hacked by poachers also looking for those animals?
Okay, thanks. So almost similar to the previous question, if you then programmed anything like that it's an endangered species being found, that data would be kept on board and not transmitted via satellite down to the ground station or directly to the ground station. That you could program to be kind of kept aside and on board.
All right, I think that's all the time we have. I get the sense that there's far more questions, but you can catch Steve during the tea break.
Thank you very much.
All right, next up we've got Stu Behop, and he'll be talking about from fields to flyways, population regulation and conservation in migrating birds.
Okay, I'd like to begin by thanking all the Oppenheimer team for the opportunity to talk here today, even if it was last minute. And I also have to come clean because I'm a pretty temperate biologist, and I'm not really going to be talking about any African ecology here, but the lessons I hope you might learn from this will be very applicable to the systems you're working in. And we've heard a lot about animals moving across boundaries and the problems of trying to manage animals that are highly mobile. And this is really kind of hopefully some of the lessons I'm going to talk about today. So it's going to be geese and swans, and they're obviously quite scary in the London Underground. So migration is a global phenomenon, and it involves the movement of billions of individuals on an annual basis. These are huge volumes of biomass moving across the globe, and they play important, and migrant birds in particular play really important roles in the ecosystems they visit across the annual cycle. So they can be predators or prey, they can be pollinators, they can be seed dispersers, they can be pests, and I'll talk a little bit about an animal that is perceived as a pest. They can be controllers of pests, and of course, they are hugely culturally significant in the regions that they move to. So they're the harbingers of the change of seasons, they feature in poetry, literature, art, etc. So an important group of animals, and migratory birds in particular, are an important group in that respect. But it seems that migratory bird populations are in crisis, so we've seen lots of stuff like this. We know we're losing birds at an enormous rate, probably billions of individuals since the 1960s. Top panel is one for Northern Europe, for Afro-Palearctic migrants. The bottom panel is North America. They're estimating 800,000 birds per square kilometre going missing over 10 years. These are astronomical losses. But you can see from that bottom panel it's not uniform. And this, we have some species increasing in number, some migratory species. Some species like this willow warbler, this is a BTO plot of willow warbler population trends in Britain and Ireland. In the southeastern part of its range, the grey, it's declining. In the northwestern part of its range, Scotland and Ireland, it's increasing. Diagnosing the causes of these things is quite tricky, particularly when we only got population level estimates. Beyond the kind of obvious, there's climate change and habitat change going on. And it's even more complicated because the responses to changing environment vary among species, vary among populations, vary within populations in time, and vary within populations in space. So it's a highly complicated issue. And this is some work one of my postdocs did a few years ago, just to illustrate that migration is a costly behavior. So we did an analysis of life history traits in migratory animals, both mammals and birds. This is just the bird data. All you need to know is that bottom axis is a measure of the pace of life. So lifespan, age of first reproduction, number of offspring they produce. And you can see full migrants, which is FM in the top, have a faster pace of life than partial migrants, which in turn have a faster pace of life than residents. So migration is probably costly because it's shaping the life histories of these animals. And of course, we can interpret this in two ways. This may mean that these migratory animals are kind of on the edge because they're living this highly energetic lifestyle, and so additional insults may cause problems for these populations. But of course, those higher reproductive rates may also mean that they can buffer better the effects of change as it happens. So it may be a response to living in these stochastic environments, because migrants have no real way, that we know of anyway, of predicting the places they're going to, or the conditions of the places they're going to end up in. And the conservation of migrants is tricky. For a number of reasons, I'm only going to talk about two of them here, otherwise I would be here till the end of the day. One of them is, for some time, ecologists tended to teach the annual cycle of animals as a series of black boxes. But we've known for a while that actually what you can achieve in one season is inextricably linked to what you did in a previous season. And in terms of migration, we call these processes carryover effects. So something like this European, oops, sorry, I didn't mean to do that. Something like this European roller, wintering in East Africa, may settle in a really good territory, get loads and loads of insects during the winter months, and that allows it maybe to migrate early back to Northern Europe or have more resources to devote to reproduction when it gets to Northern Europe, and as a consequence, it increases its fitness. And so we could be looking at variation in roller productivity in Europe, going, well, what's going on with the breeding grounds, when actually it's a phenomenon that's been driven by resource access during winter. So these carryover effects could act as mechanisms of regulation, and it means, again, diagnosing decline of populations is really difficult. The other obvious problem is that migratory animals, and migratory birds in particular, do not recognize national boundaries. So many countries are important to single species, and they're quite often, the protection given to these animals quite variable across the range. So this is a pink-footed goose. It breeds in Greenland, where it's shot in relatively low numbers. It stages in Iceland, where it's shot in relatively high numbers. And then it comes to the UK for the winter, where it's shot again. So it's been harvested on multiple occasions across that annual cycle. And we do have conventions. We have the Convention on the Conservation of Migratory Species, but individual countries will enforce derogations to those laws because these animals are pests. Protection is poor or non-existent in other countries. And so we have this system where we have animals visiting lots of places, lots of different designations, lots of different protection or exploitation. And so really to try and get a picture of this, we need to understand who goes where and when they are there and what time of year they're there. And this is why individual level data are really important. So individual level data are obviously fine-scale data compared to counts of animals, which are a typical way of censusing populations. And I'm not suggesting population censuses aren't good. They are very useful for a number of things. But if we have fine-scale data, individual level data, we can start to pinpoint carrier effects because we can look at the conditions an individual has experienced at one point in the annual cycle and then look at the vital rates in another. We can explore the consequences of different strategies individuals are taking. We can look at how habitat use influences fitness. We can look at routes. We can look at annual variation. And of course, all of those allow us to then start pinpointing mechanisms of change and mechanisms of decline. And of course, that will allow us to identify where population regulation occurs, and that then allows us to enforce targeted conservation efforts. So the problem's solved. We just need individual data. But of course, these animals are traveling huge distances, very difficult to track. One of the main ways we've really revealed the richness of migration, certainly of birds from the northern hemisphere wintering in the southern hemisphere, is via ring recoveries. But ring recoveries are it's very difficult to set up individual long-term data sets with ring recoveries. These are the metal bands we put on rings. The recoveries of these animals tend to be serendipitous. They're often dead, which means it's very hard to know what to make of, and they're often very rare. And I've just got a wee quiz for you. This is a pied flycatcher. 650,000 pied flycatchers ringed in the UK since about 1900. Anyone want a guess at how many sub-Saharan African recoveries there are? What was it? What did you say? You're right, it's 5. 5 sub-Saharan African. So if you think about it, there's nothing you can make of that. 650,000 and 5 recoveries. So ring data do not, or this kind of conventional ring data is not the best approach to generate these individual studies. Of course, we've had this technological revolution, and we've seen plenty of examples. We just saw an example of further technological revolution. And it's a huge impact on our understanding of the migrations that animals undertake. But the size of the tags are really too big for a lot of the animals we might be interested in. This is a study we did, a meta-analysis we did a few years back, showing that really no matter what size of tag you're putting on a bird, it does have detectable effects. And typically the sample sizes are small, because if we're tagging 20 individuals of a population of 10, 15,000, it's very hard to know what to make of the responses we observe. So there's still huge knowledge gaps here. And I'm going to try and persuade you that migratory wildfowl overcome a lot of these things, and as such can provide really good insights into the processes that are regulating migratory species and how we might tackle some of the problems that they face. So I'm going to talk most about geese and swans. This is a light-bellied Brent goose. We can catch them relatively easy. This is a cannon net we shot over birds. We catch them in the nets. We fit highly visible color rings to them, and then we can recite them at later dates, so we don't have to recapture them. So this is AKON with its partner NVON. We know these two individuals very well. We ringed these birds in Dublin. We saw them again in Iceland. So they're easy to recite partly because they tend to be very faithful to sites, so we can go back to the same sites year in, year out. And because they live together, we can assign long-term pair bonds, so we know who's paired with who, so we can start to build lifetime histories of individuals. Another really neat feature is they have extended family parental care. So getting these things breed really far north. It's very hard to get to their breeding grounds, but they come back with their offspring. And if you look carefully, you'll see some of these birds have little white bands on their greater covers at the end of their wings. Those are the juveniles. The ones without the white bands are the adults. And we know the juveniles hang around with the adults for about 11 months. So as long as we see the adults, we can know whether those individuals had a successful breeding season or not, and obviously how many offspring they produced. And another neat feature of them is we can measure their instantaneous condition remotely. We don't have to capture them, because these birds, all of these birds, store fat between their legs and their tail. And this we call the Abdominal Profile Index, or API. And these measures are highly repeatable among individuals. So I am talking about individuals measuring them. So we calibrate off one another. And of course, we've then taken these measures and they correlate with body mass, they correlate with the diet they're having. So we know they're measuring something about the condition of the animals. So, well, Phil, to the rescue for migratory birds. These features allow us to link up the annual cycle. They allow us to build accurate demographic models. We can then relate changes in vital rates to events and decisions in these animals' lives. And of course, that allows us to identify where regulations are occurring. So I'm going to give you 3 case studies, 3 beautiful birds. The light-bellied Brent goose that I've been working on for about 25 years. Greenland barnacle goose, another long-term data set, only been working on that about 10 or 15, and whooper swans. So light-bellied Brent geese undertake this migration. They are wintering around the coast of Ireland. And about late April, the birds leave Ireland and migrate up into Iceland, where they will spend about a month gathering all of the resources they need for reproduction. So this one you'll see start foraging. They're foraging mostly on the marine angiosperm zostra eelgrass. And they cross the Greenland ice cap into the high Arctic. 470N breeds successfully. You'll see from the track it just stops. That's it nesting. And we know 470N bred successfully because we saw it with its offspring. And then they come back in the autumn. So for these birds, fat stores is the key driver of their annual cycle. They're social foragers, so they're foraging in very large groups, fighting with one another, and there's very predictable dominance hierarchies. So family adults are dominant over pairs, and they're in turn dominant over singletons. They also prefer, as I alluded to, these marine plant resources. So this panel on the bottom is work that Rich Inger did back in his PhD. We've done this dozens and dozens of times. No matter what measure of body condition you choose, it correlates with the amount of marine protein in the diet positively. So this marine protein is estimated using the stable isotope analysis of blood. And this is just body mass in this instance. But as these resources get exhausted during the winter months, they do switch to terrestrial foraging, which is not as profitable. They're time limited. We found birds in nests 500 miles from the North Pole. They're really getting up about as far as it's possible to breed for a vertebrate, and they've got virtually no time to lay a clutch and get offspring to independence before the snows of winter come. So they're time limited, which means they can't buffer the effects of a bad decision at one point in the annual cycle very well. And of course, they're capital breeders, as I alluded to. They're carrying everything into the Arctic with them, because when they get to the Arctic, there is nothing. I assure you, you've been up there and you kind of look around, you're thinking, I don't know how these things are surviving up here. So this plot here, when it first appeared during Rich Inger's PhD some time ago, was a bit of a surprise to us. This is the amount of marine protein in the diet of adults who are families versus pairs of birds. And surprisingly, the family adults have less marine protein in their diet late winter than the pairs. And what this means is those family adults are in much poorer body condition than pairs, despite the fact that the family adults should be able to monopolize resources. They're dominant over pairs. And what is happening here is a multi-seasonal carryover effect, starting with successful breeding. The bottom panel on the left here is Zostra at low density. The top panel is Zostra at high density. When the geese return the Zostras at high density, they graze it down. it turns out the juveniles just cannot forage on zostera at this low density, and what they do is they drag the adults onto terrestrial habitats because the juveniles can maintain body mass on those habitats, because then there's not much, it's not very hard to forage on swaths of grass. This depletes the adult body condition, delays their migration, and as a consequence, they end up late on the staging grounds, late on the breeding grounds, and that results in very few of the adults in our population being able to breed in consecutive years. But reproduction is highly variable across years. So the top panel is the percentage juveniles in the flocks. And you can see there's total crashes in some years. And this is quite a typical pattern for Arctic breeder. And of course, the smart ones of you would think, well, it's clearly lemming cycles that's driving this. There are no lemmings where these birds breed. So we suspected that these mass breeding failures were associated with weather. And one of the smoking guns is the North Atlantic Oscillation, which is I think it's about 10, 11-year cycle, very similar to El Nino or the Ensign Oscillation. And we can see it has peaks and troughs. And so NEO in late June really reflects that window when the birds are coming into the Arctic and starting to breed. So we suspected that would be the best place to look. And this is what we found. So this is what Zav Harrison did during his PhD, where our prediction really here was that the weather's probably delaying or preventing breeding. These positive NEOs mean adverse winds and snow, and if there's snow on the ground, the birds can't lay eggs. Negative NEOs are good. So this is the model that Zav built. The x-axis is a measure of body condition. The y-axis is number of offspring. And the model actually predicts the number of offspring quite well. And you can see the red line is those bad years. And birds are not managing to produce very many offspring in those bad years. In contrast, the blue line is the good years. And so what we see is the variation fitness within years is being explained by this density-dependent carryover effect, whereas the variation in fitness among years is a density-independent abiotic effect. So what does this mean for the population and where regulation's occurring? So we've got a huge database of those birds, about 300,000 resightings of these individuals over a long time period. So Ian Cleasby, as part of one of his postdocs, built an integrated population model, which essentially includes all of those aspects, include behavior, weather, demography, and the annual counts. The top panel, the red dots are the counts, the black line is the model. You can see the model's fairly predicting our count data, our empirical count data, pretty well. So it turns out, as the bottom panel shows, that the female survival is actually lower in those good breeding years. So this might be some sort of reproductive trade-off. Might be allied to the kind of thing Andrew McKechnie was talking about yesterday. It might be thermoregulation, we're not really sure. So the population is currently regulated by a winter-driven carryover effect, that fat score as birds are leaving. But population change is really most sensitive to adult survival. And I think what we're concerned about here is, as the climate ameliorates, these stormy springs or these clear springs might become more common. And if we get system flips, i.e. we start getting lots and lots of reproductive years, then the system may flip from a winter-regulated system to a breeding season-regulated system. And of course, that's huge implications for how you conserve this population, because at the moment it's pretty easy. If you want to conserve them, we just protect winter habitat. But if it flips to a summer-regulated system, it's actually going to be very difficult to do anything for them. I'm now going to talk a little bit about how local management actions might drive flyaway scale effects. So these are Greenland barnacle geese, a rather similar migration, wintering in Western UK and Ireland, staging in Iceland, and then breeding in East Greenland, sorry. This is work that Amy McIntosh and Luke Osnov-Harris did as part of their PhDs. So barnacle geese are a conservation success story. They basically went from threatened to agricultural pests in about 40 years. And that's because of the change in agricultural practices. In Northern Europe, people effectively are farming for geese. Geese love the way farmers manage the land up there. So intensification has been brilliant. It's been bad for a lot of things, but it's been brilliant for geese. And on the island of Islay in Scotland, the population increased from 2,000 to 50,000 individuals, right? So it's an absolutely dramatic increase. And of course, this has led to conflict with farmers, because These birds are grazing pasture that are either being grown for silage or livestock production. And the geese reduce yields, but they also actually destroy the pasture through trampling, so they're a real problem. This bird is protected under the African Eurasian Migratory Waterbird Agreement, but there's the UK have given a derogation to that to shoot birds that are on these high-value reseeded fields to manage the population. However, the derogation was given on a rather back-of-the-envelope calculation. They just said, well, we think it should be about this, you should. Nobody really actually modelled this. And of course, the birds are actually being shot in other parts of the range because they're a pest in Iceland as well, so they're being shot there. So there's a need for coordination across range states, and there's a need for us to coordinate conservation and management. So we got commissioned by the Scottish Government to build another integrated population model that would incorporate data throughout the whole flyway to allow them to inform their future management of this population. So the model is very similar to the Brent Goose model. It has a breeding census, we have a demographic model that's got the mortality in it, we have productivity estimates, and then the difference here is we've got the harvest because we know the bags that are returned in Iceland and Scotland. And you can see again, in this one, again, the counts are the dots, the lines are the predictions, the model's fitting the data sets very, very well. So the top line is the entire population, which is a 5-year count. The blue line is the Isla population, which is an annual count, and the orange line is all the other sites, which is also a 5-year count. And you can see that 2011 is when the derogation happens, and the population starts to decline as soon as shooting is introduced. And indeed, when we look at the harvest rate of birds, so you can see the Iceland harvest rate is relatively constant, but that Scottish Isla harvest rate suddenly shoots up about 2011. I'm not going to talk about these, but these are the kind of predictive models that the Scottish Government are now using to think about management. We can run different scenarios and look what happens to that population. We can run different management scenarios. So it's informing future management scenarios. The key message here, though, is that changing a vital rate at a single site is driving the population trajectory of this whole flyway. And of course, that has profound implications for conservation efforts. So we need to be sure that site-level management prescriptions are not affecting population-wide conservation goals. And I'm going to finish with arguably the most beautiful of the three, which is the whooper swan, Icelandic whooper swan. This is work led by Andrea Soriano Redondo. So these don't have quite a big migration. They winter off the British Isles, and then they migrate up to Iceland to breed. And the red, this is in collaboration with the Wildfowl and Wetlands Trust in the UK. So the red dots are Wildfowl and Wetlands Trust reserves. So the reserves, again, were sited where the swans were. They just thought, well, there's lots of swans there, build a nice reserve. We've got some coffee rooms, people come in and watch them. And the assumption there is that the regulation of these populations is happening at the wintering sites, okay? And they've had massive marking and individual ID programs on these swans over about 30 or 40 years, so there's a fantastic data source there. The birds are fed at the site, so we think that's probably a good thing. And there are predator fences at the site, so there's eventually a couple of things that should be good for these animals. But there's lots of evidence that protected areas aren't working the way they think they are. And there's a recent big analysis in Nature where they showed that protected areas have a very mixed impact on waterbird populations. So the goal here is really to try and help the WWT work out whether these protected sites are actually functioning in the way they hope they are. So there has been a population increase. The question they are asking is it increased because of the reserves? So it's increased by about 5,000 over 10 years. We've got this huge reciting database. We've got productivity assigned to those pairs, so we can build a demographic model there. We build a survival model. This is just one of these multi-state survival models. We don't need to go into the detail of it. All we need to know is we model survival inside the reserves and outside the reserves together, and we model the survival of juveniles, immatures, and adults separately, okay? And then we can take this data and build population projection models and forecast what we think the reserves are going to do down the line. So the first result was exactly the result the Wildlife Literature Trust did not want to see. Turns out that the birds inside reserves have lower productivity. So they're much less likely to come back with offspring than birds outside reserves. And it's not about who uses reserves, because if you look at birds that move into reserves end up with the same productivity as birds that are staying constantly in reserves. So this suggests it's nothing to do with the individuals that are actually occupying the reserves. But productivity is not everything. Turns out survival is much, much higher inside these reserves. So you can see for all age classes, survival is higher inside reserves compared to outside reserves. And what that means is birds that spend their entire lives inside reserves have much higher lifetime reproductive success. So the reserves are working. The WWT are pleased. And we can take these values and project them into the future. What we find is that the growth rate inside reserves is faster than the growth rate outside reserves. And actually, reserves may contain up to 50% of the population by 2030. So that contrasts with about 5% of the population in 1985. And we think the enhanced survival is likely linked to reduced predation, and actually they tend to have, one of the main ways these swans die is with collision with power lines, and these reserves tend not to have power lines going through them. So you only get this level of detail with these high-resolution, long-term individual studies. And so the conclusions at the top are just the main ones about what I've talked to you about, but I do want to try and persuade you that these principles are not exclusive to ducks and geese, right? Any animals that are engaging in long-distance movements are likely to be affected by the same kinds of processes. So I'm thinking particularly elephants, but vultures, antelopes, fish stocks is the same problem. You know, we're having fish stocks on one side of an ocean basin differently to the other, and it's effectively the same stock. And I think, just in general, if we're managing highly mobile species, it requires these integrated multi-scale approaches, these high-quality data sets, obviously ecological insight, and then some sort of coordinating governance. So I thank you very much for your attention. I obviously said we, but it was actually they. So thank you very much for your attention. I'll happily take any questions at this time. Thank you.
Thank you, Stu. Any questions? Surely. Concerns, complaints, suggestions? Nobody? Oh.
There's one way up the back.
Yeah.
Hi, thank you. This is Sally Archibald from Wits University.
Thank you,
That was
Sally.
really fascinating.
Thank you.
Good to know the reserves are working for the swans. But could you tell me why they're not working for the other birds in the paper that you mentioned?
Well, I think actually part of that, the reason in that analysis is that it's census data. So it's just count data that they're using, and it relax some of the nuance that that these kind of high-resolution data sets can allow us to get to. And I think also a lot of these sites, a lot of these wetland sites are in marginal lands that are next to industrial plants, and they might, if you're, I guess it's the same in this part of the world, a lot of the reserves are in places that people don't want to use, and I think, again, they're probably just not very high quality, a lot of them. That would be my guess, Sally, but I'm not sure.
Great, thank you.
Thank
If
you.
you've got any other questions for Stu, you guys can migrate to the deck. Alternatively, if you're feeling extra goosey, you can spread your wings and flock to the bar later. At the end of the day, what's good for the goose is good for the gander. All right, all right. Okay, enough of this, enough of this. All right, up next we have Tinao Petso, and she's going to be talking about improving AI for wildlife tracking, the value of expert tracker knowledge and training data. I'm done, I promise, I promise.
Good afternoon, everyone. My name is Meja Pizzo. I'm a PhD student and I'm also serving in the military in Botswana. I am supervised by Professor Rodrigo Jamisola and Dr. Namusha Mlaleza from Botswana International University of Science and Technology, and I'm also co-supervised by Dr. Zoe Joel and Dr. Sky Alibahai, and they are the founders of WildTrack. WildTrack's mission is the development of non-invasive wildlife monitoring techniques for conservation. And we also have Captain Waja Mereki from Botswana Defense Force. Our research is titled Improving AI for Wildlife Tracking, the Value of Expert Tracker Knowledge and Training Data. And we are funded by United States Army and Botswana Defense Force. We quickly like to share one of our latest publications titled An Investigation of Lightweight AI Models to Classify African Ungulate Species from Tracks. So one of the main contributions of our research work was the development of introducing the use of bounding box to classify African ungulates in terms of with bounding box to classify the track, and also using landmark points. Additionally, this work, we trained the models in the lab, and then we went back into the field to test how the model performs using a laptop to understand efficiency and its challenges. In our field testing data, we managed to achieve an accuracy of 98% in classifying African ungulate species. And these species that we looked into were black rhino species, blue wildebeest, common eland, giraffe, white rhino, and zebra. Why African ungulates? African ungulates help in maintaining the ecosystem integrity and balance, and they do also help in ecotourism as well as in the cultural value as African people. Artificial intelligence is something that is mostly used nowadays in our everyday activities, and it can assist or aid us in terms of anti-poaching efforts. Like Anne said, I work in Botswana Defense Force, so our main or priority reasons that we contribute to in support of my country is in the anti-poaching aspect. And it additionally can help in issues such as human-wildlife conflict mitigations and also in wildlife monitoring efforts. For this research work, we looked into 3 research areas in Botswana. We considered Khama Rhino Sanctuary, which is situated in the central district of Botswana. And this place has both soft and hard substrate, and it has 4 species. It has several species, but for our analysis, we only looked into 4 species, which is black rhino, blue wildebeest, giraffe, and white rhino species. Additionally, we visited the second place where the substrate is hard, which is Mokoloji Nature Reserve, which is situated in the southeast portion of Botswana, and it had blue wildebeest, giraffe, and white rhino. Lastly, we visited the western part of Botswana in order to see where we are having a soft substrate, but this place, it only had white rhino species. Unfortunately, we cannot disclose the exact location of these species, of this research area. So our data protocol is quite simple. With the assistance and guidance of expert trackers, they help us to find fresh tracks with working characteristics. From there, we then put a square ruler, which is, you can see 2 in the image over there, and then a distance of 1 to 2 centimeters from the track. From there, we put a label slip. In this label slip, what we are having, we are recording the date, we are recording the name of the person collecting the data, the species, and we are recording whether it's a left hind or a right hind, and the location where we are collecting the data. From there, then we take an image, making sure we make inclusion of the ruler and the label slip. We collect as many footprints as possible with the guidance of expert trackers. Additionally, we record the environmental conditions where we collected that data, and aspects such as lighting effects, the type of substrate, and the specific location of the trail where we collected the data. These are just a quick visualization sample to show the effects of different weather seasons in terms of dry season and wet season. So in wet season in my country, you are looking at a time where we are getting rains, which is around December. So the rain does have different effect to the footprint. And then we look into the dry season, which is like you are having it in winter, which is something like June. So the quality of the footprints do change a bit. What we did, we considered to see what is the impact, because with artificial intelligence, it's garbage in and garbage out. In terms of that, I mean the data that you train your model with impacts the outputs. So the model can underperform because you didn't train it with different or diverse data sets. So in this case, we wanted to see the effect where you are having two expect trackers and non-expect tracker in this case, which was me. So we went through 3,039 images individually and independently. So the first thing that we measured the track quality. We looked into the aspect, as you can look into that image, where you have region 2 and 3, which is the outer toe and the middle toe of the white rhino species. The soil is collapsing. Hence, as it's collapsing, that means certain features are not visible. So in this case, the soil collapse, we are ranking the effect of soil collapse into the track quality image. Additionally, we looked to the impact, the clarity of the outline of the footprint. So in this case, we looked into 4 regions to quantify the quality of it. Are the outlines clear? Are the outlines perfect across the 3 assessors? And we also looked into indentation depth effect of each track. Additionally, we looked into the presence of vegetation that can be, an animal will just go in any region. Sometimes it will go in a region where there is a presence of vegetation, and hence that presence of vegetation affects the quality of the track. And lastly, we looked, naturally there will also be external disturbances. In terms of external disturbances, it's regions where another animal will step on top of the footprint, or another animal walk into that footprint, because there are several animals in the area. So in this case, the image on the right is me and the other 2 trackers evaluating the images. And then this is just a quick example to show of one track that is a high quality images where the disturbances are less in terms of soil collapse, and you have clear outline and clear indentation, and there is no presence of vegetation and external disturbances. This is one image where you are having totally, this will be a low quality ranked images. There is high presence of vegetation. So one might ask, what are exactly these algorithms? So what we do to evaluate the models to see how the model perform is we looked into an image. With these algorithms, you put an image. When you put an image to the system, it will detect or localize the presence of the footprint, and it will make a bounding box. So what we are evaluating is the true ground truth of the track, which is in red box, and then we are having the model making a prediction. In this case, when it's making a prediction, it's making the blue box. So if it's an easy detection, it's something you are having with an intersection of union at 50, that means you are not having a perfect fit towards the actual track in respect to the footprint. So if you want to be tight on the exact location of the footprint, we are evaluating the mean average precision, where it's between 50 to 95, which is shown on the image on the bottom right. This is just some of the quick results. We looked into certain or different hyperparameter settings to understand the effect of our results. So the results in here, we are analyzing where you are having mean average precision, which is a kind of a loose detection, not a tight towards the footprint. So in this case, we looked, the blue parts are the results or analysis based on the images that were analyzed by me or assessed by me, which I'm a non-tracker. And then we increased the images gradually. So we had 100 images for the left hind, 100 images for the right hind. And in that case, you are having 200. And since we are having 4 species, that makes a total of 800 images. We further increased the images to 150 images per class, which makes a total of 1,200. And then further increase with 50 images to see the impact into the model. In this case, we are having a total of 1,600. So the green and the red results are for the tracker's results. So here quickly what you can see or analyze, you can see that the results are based on the trackers on the red and the green. Has a higher performance compared to the results of a non-tracker. For me as a non-tracker, I would have to train the model with higher number of training images. We further looked to see if this impact still relates where you are making sure that the track is properly on the footprints. And similarly, we got the same idea that we got the same results that the non-tracker, you will need more images, whereas for the expert trackers, you will need lesser images in order to achieve high model accuracy in species classification. These are just quick images under different environmental settings that we tested with the highest or the best performing model from the analysis. We have the middle images after rain condition. Out of this, what we can realize is expert trackers, which is traditional ecological knowledge, is quite vital in data collection in our study. So they are quite valuable to have. And for the data pre-processing, additionally, it does highlight that with expert trackers' help, fewer images are needed to achieve high accuracy. And for a non-tracker analysis, you will need a higher number of accuracies in AI model development. Tracking is something that is quite important, and it should be utilized in research and incorporated. As I'm from the military, we use tracking skills for our anti-poaching operations, and it's a useful skill to keep improving. We would like to thank some of the trackers that contributed in our research work. And mostly of these trackers, 90% of them are serving in the military, and 10% are working in national reserves as trackers. Thank you.
Thank you, Tanao. Any questions?
Thank you very much for that presentation. So I'm just curious to know which specific AI tools are you using for your work? Are there any specific? Because you just said improving on AI in the prediction. Are there any specific, for example, the convolution network? Are you using such kind of tools that or models?
I'm not sure if I understood your question. Tools, you mean the devices that you are collecting the data with? Or you mean the computer?
The algorithms. I mean the algorithms, for example, when you talk about AI, it's a bit general.
Yep.
So are there any specific AI tools that you're able to tell us that you're using in your work? Is it neural networks, tools related to neural networks, for example?
Oh, we are using deep learning. Thank you.
Thank you very much. Two short questions. The first one is, how does time of day affect the model's confidence in determining what the track is? And the second one is, does the model get any false positives? Thanks.
Okay, thank you. I think you can repeat this. I'll answer the second one, and then you repeat the first one. Okay. We do get false positives, and that happens a lot between black and white rhino species. To account for that, when we did our first study in the publication that we had, we end up going to use strategic landmarks. And when we use strategic landmarks, that's when we improved the model performance. So we use strategic landmarks because it's something that WildTrack has developed over years, but using statistical morphometrics. So we enhance that in terms of putting it in AI to see the effect. Hence, when we put the strategic landmarks, the results improved. The first one, I didn't guess what.
The first question was, how does time of day, in other words, the amount of shadow on your track, affect the model?
Okay, thank you for that question. We collect our data during early morning and early afternoons, but we did make an observation that when there is lighting and shadow in the same image, there seems to be a challenge. Sometimes you get lower model performance. So it's something that we are still working on. But we do acknowledge that environmental factors in terms of the lighting and shadow effects, especially where there's light and shadow, do impact the model performance.
Thank you very much for your very interesting presentation, and it's really exciting to see people from the military doing this kind of research. I wanted to find out what risk management and mitigation measures are you thinking about in terms of the potential of these same tools and approaches also being employed by the enemy that you're trying to also fight, like the same technology, especially if it's open source, being used by the poachers so that they are also more efficient on their poaching? Thank you.
Thank you for the question. It's quite a good one. Actually, I'm a junior officer. In between junior and senior officer, I'm a major. So there were certain precautions that were taken. There was a meeting between Botswana Defence Force, which is my employee, and Ministry of Environment and Tourism. They had to confer that I hold the data, and everything that we do before we can share it further or do anything further with it, a decision has to be made. So at the moment, we are trying to protect the data being held by the people who work with the data in terms of that. But in terms of when we visit these areas, we also have to write in advance requesting so they know who are the exact people collecting data in that area at the time it's registered. So they're keeping records of us who are collecting data. Additionally, in order to develop this model, you would need a lot of raw data in terms of that. So the poachers can develop the model in terms of making it open access, but you need a lot of data under different areas of analysis. But for this case, the decision lies between Ministry of Environment and Tourism and the Botswana Defence Force.
Okay, thank you, Tanao. We're not going to take any further questions. If you do have further questions, you can track her down later. Okay, up next we've got Thando Twala talking about ecophysiological responses and projected climate suitability of the podocarps.
Okay. Afternoon, everyone. Sanbonani. As already mentioned by Wendy, today I'll be talking to you about podocarps and their response to climate change. But I just wanted to highlight first that this is my PhD work, and I spent most of my academic life as a savanna ecologist, so all of my training is there. And I eventually got very tired of exploring that side of the world, so I decided to challenge myself by going to a different ecosystem. So yeah, I'm learning. I came out with a lot of questions. I'm sure many people who've done research start off with a question and come out of that with more questions. So this is some of my work. It actually came from or was inspired by a paper by William Bond, where he spoke about this ecological competition, right, that happens in forests where you have your tortoise in the form of angiosperms, in the form of gymnosperms, and the hare in the form of the angiosperms, where the hare is fast-growing, competitively dominant in these high nutrient ecosystems, and because of these traits, they tend to outcompete gymnosperms in these systems, where our gymnosperms are the tortoises that are slow-growing, shade-tolerant, and very persistent, and they thrive in these suboptimal conditions. So essentially, these characteristics and how they respond to light and nutrient stress is what shapes our South African forests. So South Africa's native tortoises, as I've mentioned, are the gymnosperms, where in South Africa, the most prominent family are the Podocarpaceae, or the podocarps, which are the yellowwoods, and they are a national tree. So they are very central to Afro-temperate forests and sort of influence and shape the structure and the function of our forests. These forest systems tend to occur in very fragmented relic spaces, and they stretch from the eastern escarpment going all the way down to the southern Cape, with this distribution being shaped by millennia of fires, topography, as well as climate. However, as many of the talks that we've seen between yesterday and today have spoken about, the imminent challenge of climate change, because now it's happening more rapidly than before, with heat and drought stress being the biggest drivers or biggest factors. And it's very nice because Prof. Andrew actually spoke about hotbirds, and he highlighted that this is also an issue in forests as well. So now the race is not solely based on competition for light and nutrients, but now the next thing that we need to also look at is how can these species in these forest systems cope with drought and heat stress. So persistence of these species depends on their ability to physiologically respond or through physiological thresholds, as well as their reproductive timing and demographic resilience. And this brings me to my question, which was if or can these species that actually persist through a strategy of to persevere at slow and steady, using a slow and steady strategy, will they be able to cope under the stresses when the competition rules are rewritten by unprecedented climate change? So how I did that was that I firstly tried to predict, or I tried to map or predict the potential distribution of podocarps in South Africa, or habitat suitability, under current and future climate scenarios, as well as exposing seedlings to climate change-related stresses, because William Bond has stated that this competition is very prominent at the seedling stage. So together, all of this gave us a more mechanistic way of looking at the system. I hope you guys will be patient with me, because I'm also still trying to figure out the threads of putting all of this together. But we can journey together and try and figure it out. So starting out, what I did was I selected 2 of the 4 South African podocarp species, the first being Podocarpus henkeli, which, if you can see there, we have the GBIF data that I downloaded, and Podocarpus henkeli is represented by the orange dots, and then Afrocarpus falcatus, which is represented by the blue dots. After that, now that we had our occurrence data sets, I downloaded climatic variables from CHALSA, and I ran a correlation to be able to remove variables that were correlated with each other. Upon completing the correlation, we were left with 7 climatic variables, which were maximum temperature of the warmest month, temperature annual range, mean temperature of the wettest and coldest quarter, which made up our temperature variables. Then we also had precipitation of the wettest, driest, and warmest quarters, making up our precipitation or rainfall variables. Now that we have our occurrence data sets and our environmental data sets, we fed this into an R package, which is BioMod2. I chose to use an ensemble model instead of using one algorithm, because ensemble models were considered, or are still considered, in fact, to be more robust than using a single model. So these models that you'll see here were actually informed by 10 algorithms. From there, the output was to look at the current distribution or habitat suitability for both species in South Africa and identify environmental variables that drive this distribution. Secondly was to map or predict the potential future habitat suitability of these species for 2070, so I didn't want to push it too far to 2100. And what I did was I checked, I looked at change in climate change at 2 climate change scenarios, which were RCP 4.5, sort of like average climate change, or moderate climate change, sorry. And then lastly, RCP 8.5, which is sort of like worst case scenario. So just to take you through the results for the current predicted habitat suitability for Afrocarpus falcatus on your right, you'll see that habitat suitability spans from the northern parts of the country going all the way down. If you know forests, and as I've already mentioned in my introduction, is that this is tending to overestimate. But it makes sense because this is a correlative model and not a mechanistic model. So we're just looking at habitats based on climate, showing habitat suitability. Moving on to Podocarpus hinkeli, we can see that the distribution is in a very summer rainfall area, sort of isolated in the eastern parts of the country. So the distribution of Afrocarpus falcatus was influenced or driven by precipitation of the driest month. And when looking at this, just to try to link these variables with its ecology, I assume that this variable is important because it ensures, during this period, it ensures that the seedlings are able to survive during the dry periods, and secondly, that there's successful cone development as well as pollination during this time period. For Podocarpus hinkeli, with precipitation of the warmest quarter being important, it might be due to increasing successful seed formation because podocarps actually produce seeds that are underdeveloped, and to help with seed maturation. And these results actually correlate with a lot of studies that have been done by other scientists, such as Tim Broadrip, who's looked at podocarps in Australia. And most of these results or most of the patterns that we saw was that it was due to sort of the plants having small single-veined leaves, as well as due to their hydraulic structures, because unlike angiosperms, they don't have separate structures for water transport and for support, as well as due to their seed biology, because podocarps tend to produce recalcitrant seeds, which are seeds that lose viability when they dry down. So I took the future predicted distribution of these species, and I overlaid that with the current distribution to sort of look at the change or potential change in habitat suitability with climate change. So you'll see that for Afrocarpus falcatus, that the distribution remains relatively stable. But what's interesting is that you can see that we're gaining suitable habitat at high elevation. And this is driven by temperature annual range. Moving on to Podocarpus hinkeli, you see quite a different distribution, where unexpectedly so, in moderate climate change, you can see that with the predicted habitat suitability is expected to be lost at higher elevations, and this is driven by mean temperature of the warmest month. So indicating that those higher or upland areas are predicted to become hotter. However, in RCP 8.5, you can see that the areas that were initially predicted to be lost or contracting are actually stable habitats. And you're actually seeing that there is potential shift upslope and shift downslope. And this pattern or this distribution is driven by precipitation of the warmest quarter. So this precipitation in this case is clearly offsetting the higher temperatures that you're seeing up in the RCP 4.5. So to switch gears now, moving from predicting habitat suitability or distribution, what I wanted to do was to sort of push them to the limits to understand their physiology. Is the physiology driving their distribution, or also restricting their ability to compete potentially under climate stress? And what I did was, with the same species, I purchased seedlings that are from the same seedling batch of the same size, and then I brought them into the greenhouse at Wits University, allowed them to acclimate, and then I tested their limits. So what I did was, I looked at temperature or ambient temperature in the distribution of Podocarpus hinkeli, which, as you've already seen, tends to overlap with the distribution of Afrocarpus falcatus. So I chose 3 temperature treatments to test its response or their responses to temperature, and the first being ambient temperature, the second being 2 weeks of ambient temperature, 1 week of high temperatures, and 1 week to recover or at ambient temperature, and then lastly, pushing them at high temperatures. And of course, you cannot have a climate change experiment without introducing a bit of drought. So I further in the individual temperature treatments, I subdivided the seedling batches into 5 seedlings that will be well watered for each species and 5 seedlings under progressive drought. So I'm just presenting just a subset of some of the variables that I actually measured. Firstly, we looked at photosynthetic traits. So we looked at chlorophyll content using a SPAD meter, just to use a non-invasive methodology to measure chlorophyll content, maximum quantum efficiency of photosystem 2, which is sort of a gauge of plant health. And then I measured whole plant transpiration by using gravimetric method of measuring water use efficiency. And then lastly, I used a visual way of looking at leaf production as well as leaf aging throughout the experiment. I just wanted to highlight that this was sort of a snapshot. It's not a long-term study. It was a short-term study over 4 weeks. So looking at some of the results, you'll see that, interestingly, Afrocarpus falcatus increased its water use efficiency under drought stress, and this shows that the species is plastic, but it's also very sensitive to drought, especially at high temperatures. But what's interesting is that this plasticity actually coincides with its distribution. As you've seen, it occurs in both high rainfall areas as well as in dry coastal areas. So that's an adaptation to episodic drought. However, looking at our restricted species, Podocarpus henkeli, you'll see that the well-watered, the water-stressed seedlings actually increase water use efficiency under drought stress across all the temperature treatments. And this could possibly be due to stomata regulation as well as photoprotective mechanisms in order to protect the functioning of photosystem 2. So I actually have students that are measuring other traits in relation for us to be able to understand whether this is actually the case in terms of stomata regulation. So then looking at chlorophyll content, I know these graphs make a lot of sense. So we can see that chlorophyll content under drought stress actually decreased across all the treatments for both the species, which then is a proxy to indicate that there is a reduction in photosynthetic capacity for both species. Moving on to maximum quantum efficiency of photosystem 2, we can see that for both Podocarpus henkeli and Afrocarpus falcatus, there was a decrease in the efficiency or in the function of quantum efficiency of photosystem 2 under drought and heat stress. However, what's interesting is that for Podocarpus henkeli, under combined stress, you can see that there is tolerance to photo inhibition. So it is offsetting under combined stress. And then just to put it together with physiology, the physiology with the phenology, as I've already stated, chlorophyll content decreases under these environmental stresses, resulting in a decrease in photosynthetic capacity, therefore reducing the efficiency of photosystem 2, resulting in leaf senescence or leaf aging, and then at the end of that cycle, you get leaf death. So this is an avoidance strategy in order to conserve resources and to reduce the effects of the stresses. So, as I said, you guys are going to be on the same boat as me. So firstly, what you'll see is that Podocarpus henkeli, despite its restricted distribution, shows robust photosynthetic responses, and it suggests that it could also tolerate moderate climate shifts regardless of its restricted distribution. However, some of the questions I left with was, is their reproductive strategy, dispersal, and competition in these systems the true limitation to podocarp distributions? And we shouldn't be that worried about climate stress, and that while the hair actually dominates in the early successional stages through rapid growth and resource capture, do the tortoises or our podocarps persist through stress and tolerance, stress tolerance and longevity, and at what age does this happen for the seedling? So what is the bottleneck at this stage? So we're seeing that there is a shift from resource acquisition in the form of light and nutrient capture to a more stress endurance reframing, to a more stress and endurance strategy, sort of reframing the race from light and nutrient acquisition to heat and drought stress tolerance. So the question here that I would pose to you is, if people have researched, but maybe they could also help me think about it, is what are the angiosperms doing in these systems as well? Okay, so I'd like to acknowledge my supervisors, Dr. Kelsey, Dr. Jolene Fisher, and Prof. Kelsey, as well as Prof. Ed, and my funders.
Thank you, Thando. Unfortunately, we don't have time for questions. And I know what you guys are waiting for. I'm turning over a new leaf. Okay, just a quick announcement before tea, please. Yesterday, somebody in the third row from the back accidentally took the wrong conference bag, which means they left their bag behind and somebody probably took it. It had an Apple Mac charger in it, so if you got home and you found a new Apple Mac charger in your bag, it's not yours. It wasn't part of the gift. Please take it back to Ricky. It's not a name and shame, don't worry. Accidents happen. But yeah, please, if you did find something in your bag that doesn't belong there, please take it to Ricky. All right, let's go and have tea, and please be back by 4 o'clock sharp.